Hey everybody, before we jump into this problem tonight, I want to make sure, let's just make an observation about this quantity in parentheses here. 3 raised to the 2 to the n plus 1, it's always going to be even, right? For all non-negative integers n, it's always going to be even, and that's clear because 3 raised to any power, non-negative integer power, is going to be an odd number, right? So an odd number plus 1 has to be even necessarily. But interestingly enough, that would mean that 2 divides this, but we're going to show that 4, which is the next smallest even number, never divides this. Okay, that's what the negated relation means right here. Now let's take a look at the special cases. N equals 1. N equals 1 certainly implies that we end up with 3 squared plus 1 equals to 10. And again, folks, all I'm doing right here is just substituting 1 right here where n is, and you get 3 squared plus 1 is 10. And of course, that's not divisible by 4. It's obviously divisible by 2, but it's not divisible by 4. So we get 4 times 2 plus 2 plus 2 like that is equal to 10. In the presence of a non-zero remainder indicates that 4 is not a divisor. Okay, now let's try out n equals 2. Now we do n equals 2, we'll end up with, put a 2 right here, you get 2 squared, which is 4. 3 to the 4th is 81, so we'll write down 3 to the 4th plus 1 is equal to 82. And again, division by 4 leaves a remainder of 2. That's 4 times 20 plus 2 equals to 82. All right. Now, so what we want to do is just show in general that this is always the case. We've shown for the case n equals 1, n equals 2, that 4 is not a divisor of this expression. But we want to show that in general. Okay. So the first thing that's slightly tricky is to observe that 3 raised to the 2 to the n. We're just going to look at this part of it first, and you'll see how this is going to go. This part right here, I had to look at it a little bit, but laws of exponents says that you can multiply the exponents here. So you get 3 raised to the 2 times the quantity 2n, 2 to the n minus 1. Okay, it's n minus 1 as the exponent there. But notice that this is just 2 to the first here, right? And so this does give us this part right here, this would give us 3 to the 2n again, right? 3 to the 2 raised to the n. It's kind of a pain to say that, right, folks? Because you're adding your exponents here. Remember, we're multiplying like bases, and so 1 plus n minus 1 is, and let's see here, that's 2, sorry. No, we got it right. This is cool. We got this thing going on, don't we? Okay. When you add 1 to this exponent, you get n minus 1 plus 1, and we get 2 to the n right here. Okay, 2 raised to the n. Okay, it's kind of a towering sort of thing. But in any event, that's the same thing as this. Okay, that's the same thing as this. And we can actually appeal to something called the binomial theorem. Now, I've done most of the work right here. I color-coded it because I couldn't write this as big as I wanted to. But 9 is certainly equal to 8 plus 1. So if we use the binomial theorem with 2 to the raised to the n minus 1 as our power here, this is just the binomial theorem. These are the binomial coefficients. But notice that 8 is present in all the terms. 8 is present. That's the only thing that matters. These parenthetical quantities here are called binomial coefficients. They're always integers, you know. But notice that 8 is present in varying powers all the way through until you get to the very end where you just have 1 raised to a power. Okay. Now, one thing just to keep your head on straight about this is it's a lot of notation here. It looks a little confusing. But all these exponents always add up. Notice that 2 to the n minus 1 minus 1 plus 1 gives you 2 to the n minus 1. All the way across, notice how the sum of the exponents here, this 2 sums up with this exponent right here to give you the power of the binomial expansion, okay? So it's not really written like you might expect, but it's still we're still using the binomial theorem without having to introduce any other variables. But anyway, what we've shown right here with the binomial theorem is that 3 raised to the 2 to the n. Now remember, if this is bothering you, we are interested in this 3 to the 2 to the n plus 1, but we'll get there, okay? So, but what we've shown right here is that 3 raised to the 2 raised to the n is some multiple of 8. We'll call that 8m if you want, okay? 8m plus 1, right? So that means when you divide 3 to 2 to the n by 8, you get a remainder of 1. Now we are interested in 2 raised to the n and then plus 1, right? Okay, and again, I'll reference you back. The original problem is this guy right here. We want to show that 4 never divides 3 to the 2 to the n plus 1. We've just done the work for 3 to the 2 to the n, but notice that this work for 3 to the 2 to the n implies that this would be equal to 8m plus 2. Now notice 4 divides 8, right? So we're kind of in overkill right here, but this is 8m plus 2. Now if you'll reference back, we were always getting 2 up here for these 2 special cases, right? So you see that general pattern extends all the way through, all right? And you never get a multiple of, you never get the case that 4 actually divides this, okay? And that's what this statement says right here, okay? Since this is true, that means 8 never divides 3 to the 2n plus 1. Let me wrap that in parentheses, even though it's clear in context, okay? That implies that 4 never divides it. Folks, so we prove what we set out to prove. This is what we wanted to show, and we did. Now, you may be wondering, well, wait a minute here, why didn't you just go ahead and say, hey, well, we could have. We certainly could have. But this actually proves another result. This notation here, this means that 2, and we can, if you want to, we can write this as 2 to the first. Notice that 4 is equal to 2 squared, right? 4 is equal to 2 squared. So what we've really shown here is that 2 divides this expression exactly. Or I forget, I think that's how Charles Vanden Eynden referred to this. 2, the double vertical bars means that 2 divides this expression, but no higher power of 2 divides this expression, okay? We've just shown that 2 squared can't divide it, 8 can't divide it, and so 2 not only divides it, but it's the highest power of 2 that divides the expression, okay? So that's kind of a counter, or that kind of gives you some idea about the purpose of this kind of development here, because we got a stronger result than we really needed to prove what we wanted to prove. All right, folks, that does it. Hope you enjoyed. Thank you for viewing.